Okay, so we're now in a position to do hypothesis testing properly. So let's suppose we've got data x1 to xn from a multivariate normal distribution with mean, mu, and variance sigma. And critically now, we can assume that both of these are unknown. And let's suppose we want to test the null hypothesis that mu equals mu naught versus the alternative that mu does not equal mu naught. Now before, when we formed our test statistic, we looked at x bar minus mu naught sigma transpose sigma inverse x bar minus mu naught. Okay. But we don't know sigma here. So what we're going to do now is replace sigma by S inverse. And we're going to scale it as we did in the previous chapter. So we're going to let gamma squared be this times n minus p over p. And what we've seen in the previous video is that under h0 we have that gamma squared has an f distribution with p n minus p degrees of freedom. So the way our hypothesis test works is we're going to compute gamma squared obs for the data, and then we're going to compare it with the f, p, n minus p distribution. So we're going to say, if we take a name and person approach, we're going to reject h0 if gamma squared obs is bigger than the p, f, p, n minus p random variable. Let's say it's 95th percentile. Or we can compute the p-value, which is the probability that an f, p, n minus p random variable is bigger than gamma squared. Now the critical region for mu is going to be, as before, it's going to be all those values of mu for which gamma squared is less than or equal to f, the 95th percentile of an f, p, n minus p random variable. Okay. So again, because gamma squared here is an ellipse in mu, this is going to be an ellipse again. So let's look at an example of doing that. Back to our statistics and probability example we had before. So we had these 203 exam marks for first year math students taking probability module and statistics module. Okay. So let's do the hypothesis test we did before. But now let's not assume that sigma is known. Okay. So for these data, we have the sample mean was exactly 74, 62.1, 62.7. Now let's give it a sample covariance matrix, which is S here. Okay. And let's conduct the same hypothesis test. If you want to test h0 that mu is 60-60 versus the alternative hypothesis that it's not. So our test statistic here is gamma squared, which is n minus p over p, so 203 minus 2 over 2, times by, this is x bar minus mu naught times S inverse x bar minus mu naught, and this gives us an observed value of 2.84. We're going to compare this to an f random variable with 2 and 201 degrees of freedom, so p n minus p degrees of freedom, And if we look at the 95th percentile, which we can get from R using this command, we find that it's 3.04. So this is bigger than gamma squared. So we're going to find we do not reject the null hypothesis at the 5% level. The p-value here is 1 minus probability that a gamma squared is less than this f random variable, and we find the p-value to be 0.06. Okay. Now, thankfully, we don't need to do all this work ourselves in R. We don't need to compute gamma squared ourselves. There's a library that will do it all for you. Okay. So it's, you have to install it if you want to do it. So it's in this ICSNP package. But then to do the test is very simple. It's just hoteling t squared. You just put x in and what you want your sample mean mu to be. So I put mu to be 60/60 here. And what we get out is our t statistic, our t squared statistic, 2.84, the degrees of freedom, which was 2 and 201, and our p-value. Okay. And just to say that, again, this is different to what we get with 2 univariate tests. Okay, so if I do a t-test, testing just the probability scores where they're equal to 60, we find we reject H0 okay, at 5% level. The p-value is 0.032. And if we test the statistic scores, so the second column here, well, that's equal to 60. Again, we find we reject H0. So the 2 t-tests reject the null hypothesis, but when we do the proper multivariate test, we find we don't reject. And again, the confidence interval, the confidence region rather, is an ellipse, the interior of an ellipse centered around x bar. And in this case, 60/60 again just lies just inside. So just finally then, let's now suppose that we've got 2 populations. Let's suppose we've got a population of x's, x1 up to xn, and a population of y's, y1 up to yn. And let's suppose we want to test the difference between the 2 populations. In particular, we want to see if the population means are the same. So there's 2 situations described in the notes. There's the paired case, when the ith case, maybe it's a before and after. So x1 might be before a drug, y1 after a drug, and a patient 1, okay, and so on. And then there's the unpaired case, where xi and yi are independent and not connected to each other. So we're just going to talk about that case now. So I'll leave you to read the notes about the paired case. So in the unpaired case, the aim is to test whether these 2 populations have the same mean. So let's suppose x1 to xn are both multivariate normal. So let's suppose that x1 to xn is multivariate normal with mean mu1 and variance sigma 1, and that y1 to ym is multivariate normal with mean mu2 and sigma 2. Then when the 2 populations are the same, so when the sample means are the same, sample variances are the same, then this test statistic, y bar minus x bar, so the difference between 2 sample means transposed s subscript u inverse y bar minus x bar, scaled by this term here, and this has a hoteling t squared distribution with the parameters shown here. So SU here is our pooled covariance matrix estimator. Okay. So the proof of that's in the notes. I'm not going to go through it in the video, so I'll leave you to read that. Okay. So let's think about how we can use it in a hypothesis test. So again, rescaling the statistic we had before to an F statistic allows us to find a distribution we can work with. So let's look at doing this for the exam data we had. So let's suppose the students we had data on before are from 2 different programs. Some of the students are on the 3 years maths degree. Some of the other students are on the 4-year maths degree. So we're going to let the x1 to x131 be the marks of the G100 students, so they're the 3-year students. And we're going to let y1 to y72 be the exam marks of the 103 students, the 4-year students. Okay, so I plotted them here. So I've got the G100 students in black and the G103 students red triangles. And I've plotted on the 2 sample means, the 2 sets. So the question is there a difference between these 2 populations? Is there a difference between the 3 and 4-year students, at least when judged by their 2 marks in probability and statistics? So we're going to want an unpaired test here. And we're going to try and test the hypothesis that mu1 equals mu2. So the population mean of the G100 students and the G103 students is the same. Okay, and we're going to make the underlying assumption that everything's multivariate Gaussian as described in the proposition. So if we go through and compute the sample mean for the G100 students, we get a sample mean of 61.6 and 63.2. The sample variance going here. And similarly for the G103 students, we get a sample mean and a sample variance matrix. Now, the assumption that the 2 sample covariance matrices are the same looks completely reasonable. They're very close estimates, aren't they? Okay. So it looks a good bet to use the unpaired t-test. So we're going to pull the variances. So thankfully, again, there's a command for doing this in R, so we don't need to work out all the details ourselves. So we do hello telling t squared G100 G103, okay. And that tells us the t squared statistic. It tells us the degrees of freedom, and it tells us the p-value. So the p-value here is large, it's bigger than 0.05, so we're going to say there's no evidence to reject the null hypothesis.